Okay, so now let's actually talk about what is entropy. Like, what in the world is this thing? So lots of different ways to think about it. The one I like a lot, at least when you talk about like solid, liquid, gas, is molecular disorder. Okay, simply if I'm a solid, okay, I stay in the same shape. Like yes, if I zoom in here really big, what I'll find out is that the atoms, they are moving back and forth, but they're vibrating in the same spot. They have an average position that they stay in all the time. Liquids, less ordered. Now, yes, if I'm in a perfectly still environment, I'll be in the same spot, but even with that, that's the overall volume. Within that, the molecules, they're moving around a lot, even within that. And if I remove the walls, well, it spills out and it's going to take a different shape. So a lot more disordered. And finally, gas is even more disordered still, where I have these molecules bouncing around and they can go any which way they want, and they can escape gravity, can escape each other. And so increasingly disordered. Disorder is the key word here. You can also think chaos. Chaos is a word we're going to use for it. Now we can, if we want to, give a very scientific definition to entropy. This one I like to call the dishwashing problem. And I'll explain in a minute what I mean by that. So for this one, we have the total number of possible relevant microstates, and K is Boltzmann's constant. And as that increases, I get to the entropy. There's Boltzmann's constant. Okay, why do we call this the dishwashing problem? Because I wash dishes by hand, that's why, but let's look at it. So here is my dishwasher. And here's the thing. On the bottom, I've got a whole bunch of like random forks and stuff, spoons, craziness, all on the bottom. And then on top of that, I've got like a few big plates here, okay? A few big plates and maybe a large Tupperware. Now, if I want to clean dishes, I typically focus on the big things first. So I get rid of those big plates. I get rid of the large Tupperware. However, you know what's left on the bottom? A whole bunch of spoons, forks, knives, etc. So what's going on with that is that the number of items I have in here, the more items I have, the more entropy, okay? So as they go up, the amount of entropy I can have goes up. And also the number of relevant microstates. Microstates being here, how can they be configured? The simplest way of thinking about that for my dishwasher is they can either be on one side or they can be on the other. But in reality, like just them being able to change from this rotation to this rotation is another microstate. So there's a lot more chaos there. If I really want to have a less chaotic kitchen, then what I should have done, if I was going to focus on something, is to get rid of as many items as I could and keep the big things in there. And my wife can tell you that she much prefers that if I do the small things first. Or if I really want to make her happy, get rid of all of them. So big thing here is the more items you have, and items in most of our cases just like gas molecules, and the more positions they can be in, which solid, liquid, and gas gives you more positions, the more entropic the system is. Okay, is there a place where we have no entropy? Well, yes, actually. This is the third law of thermodynamics. So for a pure crystalline substance, think about those quartz crystals that you can see through. You're like, wow, I found a diamond. You didn't find a real diamond, but it looks cool. I love them too. For a pure crystal at absolute zero temperature, what you do at that point is you know exactly where everything is, which means that the number of relevant microstates is 1. And the natural log of 1 is equal to 0. So that whole entropy equation will be equal to 0 from earlier. And so this is important because we do need a reference for entropy. We need a place where we can say, okay, where's absolute 0 for entropy? And it's for a pure crystalline substance at absolute 0 temperature. That helps us out. We'll use it a lot. Now, I don't expect you to go around trying to find this on your own. It's something that you can look in the tables. It's already taken into account. But either way, just realize that what we're saying there is that those atoms are not vibrating at absolute 0 temperature. And because they're not vibrating and they're in a pure crystal, I know exactly where they are to a T, and so therefore there's no entropy. Okay. Last little thing to think about here is that entropy is a dissipation of useful work. Now, conservation of energy says that energy is still there, But it's just like these people right here. They're both pulling in opposite directions. Because they're pulling in opposite directions, they can't do any work. Okay? So when I have a heat transfer process, hot to cold, the energy is going from more useful, which is the hot body, to a cold body. And so the one that's getting hotter, entropy is increasing. The one that's getting colder, entropy is decreasing. But I'll tell you this. The delta E for the hot body and the delta, what am I saying delta E? Sorry. Delta S, the change in entropy for the hot body and the change in entropy for the cold body, if I add those together, they're always going to be more than 0. You're always going to create entropy through any process. Okay, the final place is, where do we see this? Well, a paddle wheel is a really good example of this. So the paddle wheel is trying to direct a flow. So I have a fan right here which is trying to push air in a particular direction. Now, if there was an opening there, that air will continue to go in that direction, and that's great. I've used work to direct my air, which is removing chaos. It's going in a particular direction. Now, this guy sadly hit the walls. When it hits the walls, it begins to rotate around here. It gets very chaotic. Because it gets chaotic, all of that work goes to increasing the temperature of the gas, and it's dissipated and turned into entropy. Last question you might have is there any process that doesn't create entropy? Well, in the absence of friction, raising a weight with a rotating shaft doesn't create any disorder or entropy, because you know where the weight is the entire time. So it's one of those few cases where it is, but once again, we're saying in the absence of friction. Real life, we have friction. So we can only say that this is very isentropic. It's close to being isentropic, not that it actually is isentropic. Okay, so that's it for this time. Just remember, entropy, think chaos, think more items in more possible configurations, doing less work. Thanks so much. Bye-bye.